Section 18.2 deals with peptide bonds, and peptide bonds are the same thing as amide bonds, except that when we see an amide in a protein or a dipeptide or a tripeptide, we call them peptide bonds. So an amide bond and a peptide bond are synonymous. So it says here the proteins are linear polymers of L-alpha-amino acids. The carboxyl group of one amino acid is going to be linked to the amino group of another amino acid. So when the carboxyl group of the amino acid, so the carboxyl, that comes from a carboxylic acid, of one amino acid is linked to the amino group, that comes from an amine, of course, to another amino acid, what you're going to end up doing is losing water. So when that carboxyl group reacts with the amino group, they're going to come together, lose water, and you're going to form an amide bond, or the same thing, we call it a peptide linkage. So again, I'm repeating myself, but when you have an amide bond between two amino acids, we call it a peptide bond or a peptide linkage. This reaction is a dehydration reaction as water is released. So if you take a look here, here's glycine. The R group on the amino acid glycine is just a proton, nothing more than a hydrogen. And then we have alanine over here. So the R group on alanine is a methyl group. So you can see the reaction between the carboxyl group that's highlighted in blue here, and then the amino group that's highlighted in pink over here. And the reason that these three elements are in this dashed circle is because those elements make up water. So again, when we combine that carboxyl group and that amino group, it's essentially a dehydration reaction because we end up losing water and we form that peptide bond. So our peptide bond is this bond here that's actually highlighted by the black arrow. And if I wanted to circle the amide functional group, I would have to circle, the carbonyl and the amine all together. So there we go. So that bond, that specific bond, this one here, that is what I call my peptide bond. And then if we were going to name this dipeptide, we would call it glycosalanine. So the amino acid that's farthest to the right, that's our parent amino acid. And the amino acids that precede it, we end them with a shortened version of the name, and we end it with YL. So we'll see other examples of that. So this one we call it glycosalanine. And of course, if I had alanyl glycine, so if I reversed the order of these two amino acids, I would have a completely different dipeptide. So dipeptides, it says here that condensing or dehydrating two amino acids produces a dipeptide. Well, that makes sense because 2 is signified by the prefix di. So it says here that an amino acid with a free alpha-amino group, and it's shown here protonated because at physiological pH, the amino group will be protonated. So that amino group is the amino terminal amino acid, and we call that the N-terminal for short. I like to call that the N-terminus. So not only can you call it N-terminal, you can call it the N-terminus. Okay, that's perfectly acceptable. The amino acid with the free carboxylate, so again, a carboxylic acid will be deprotonated at physiological pH, so that's why we write it with the negative charge, a carboxylate. So the amino acid with a free carboxylate group is the carboxyl terminal amino acid, and we call that the C-terminal for short. And of course, you can guess that I call that the C-terminus. Also perfectly fine. So amino acid structures are written with the N-terminus or the N-terminal on the left, and of course the C-terminal, I'll use the book's terminology, the C-terminal on the right. So whenever you're writing down a dipeptide or a tripeptide or a polypeptide or a protein, we're going to start with the N-terminus on the left-hand side like this, and the C-terminus is going to be on the right-hand side like that. So that's just a convention. So whenever you're drawing a dipeptide or a tripeptide or a tetrapeptide, you're always going to link your nitrogen followed by your 2 carbons from the amino acid, and then you're going to put another nitrogen and then 2 more carbons, and then so on and so forth. So these 3 atoms would represent the first amino acid, and then these 3 atoms would represent the second amino acid. And of course, if I had a tripeptide, I would add another nitrogen and 2 carbons, and so on and so forth. Example 18.1 is just a really nice exercise in writing the structure of a tripeptide. So the question asks us to draw the structure of the tripeptide of alanyl glycyl valine. So when I want to draw that tripeptide, you remember that we always start with the N-terminus or the N-terminal on the left, and then of course every amino acid has 2 more carbons attached to it. So in step 1, you just write out those 3 carbon skeletons. So you'll write out NCC for alanine, and then NCC for the glycine, and then of course NCC for the valine. Now we're going to make 2 peptide bonds. So we're going to have a peptide bond between the first 2 amino acids and the second 2 amino acids. So that's shown down here. And of course the second one of each one of those NCC sets is going to have a carbonyl, which is drawn in light blue. Then to round out step 2, we're going to add the ammonium group or the protonated amino group on the N-terminus, and we're going to add the carboxylate on the C-terminus over here. So another thing you're going to remember is that each one of those alpha carbons, so the carbon that's in black, is going to have a hydrogen. And then finally in step 4, you're going to add the R groups. So you'll remember, and again, you don't have to have this memorized, but alanine, the R group is a methyl group. For glycine, the R group is simply a hydrogen. And then for valine, the R group is an isopropyl group. So there you have it, a little bit of practice in writing the structure of a tripeptide. Something that's interesting about the peptide bond that we see in proteins, it says here, recall that peptide bonds are amides, and the nitrogen atom of the linkage is sp2 hybridized to allow for resonance. Well, even if you're not sure about the hybridization, if you take a look at the resonance structures here, and there's 3 of them, you'll notice that in the first 2, that the bond between the carbonyl carbon and the nitrogen is a single bond, and we call that a sigma bond. And we know that there's free rotation around a sigma bond, but in this third resonance contributor here, we have a double bond. And you would remember that there's no free rotation around a double bond. If you've ever tried making a molecular model of any organic compound that has a double or triple bond, you'll see that free rotation is not allowed. And there's some really interesting properties of peptides that result from this hybrid structure, where sometimes it's like the carbon nitrogen bond, where the bond between the carbon and the nitrogen is actually a hybrid between a single bond and a double bond. So because of this, we have restricted rotation around that nitrogen-carbon bond, and the amide is going to have 2 main conformers that are shown here. So we have the S-trans and the S-cis. Now you've probably heard of cis and trans in alkenes, and those are with respect to double bonds. But since this is drawn as a sigma bond or a single bond, so that's what the S stands for. That stands for single or sigma. So in order to rotate this bond, okay, because it does have double bond character, there's a high barrier to that rotation here. And you don't have to know the amount of energy. You don't have to have that memorized. But what you should understand is that the more stable of the 2 conformers is going to be the one where the 2 groups that are coming off of the amino acids, so these 2 big gray circles, when they're trans to each other, this is going to be the more stable of the 2 conformers. So again, that partial double bond character means that there is free rotation around only 2 of the 3 single bonds in the peptide backbone. So there's free rotation around this single bond and this single bond. And that's going to limit the number of possible conformations for any peptide. A second feature of the rigid peptide bond is that the R groups on adjacent amino acids are going to be on opposite sides of the extended peptide chain.